Hello my dear students, welcome to my channel Dey Sir's Chemistry Coaching. Today I am going to deliver lecture on important questions with explanation on the chapter D and F block elements. So let's understand. The first question is, listen, this is very important for your time, that is disproportionation reaction. What is disproportionation reaction? Actually, if we consider organic chemistry, then if molecules of same compound simultaneously undergoes oxidation and reduction, then it is said to be disproportionation reaction. For example, Cannizzaro reaction is the best known example of disproportionation reaction, where if you consider formaldehyde, it undergoes methyl alcohol, that is reduction, as well as salt of carboxylic acids, that is oxidation. So it's a kind of disproportionation reaction. But if you consider inorganic chemistry, then listen, sometimes what happens, some oxidation state of a metal becomes unstable relative to its lower oxidation state or higher oxidation state. That's why it exchange its valencies, that is oxidation state, which is known as disproportionation reaction. So let's understand the important question for your time. What is meant by disproportionation reaction in terms of oxidation state? Listen, in terms of oxidation state. So when a particular oxidation state becomes less stable relative to its lower as well as higher oxidation state, then it is said to undergo disproportionation. That is, it transfers its charges. For example, copper positive ion, that is monovalent copper, is less stable. That's why in aqueous solution it undergoes disproportionation reaction to change into divalent copper, that is more stable, and copper solid. Here the oxidation state of copper is +1, here the oxidation state is copper is +2, and here the oxidation state is copper is 0. Remember it, in any elemental state the oxidation state always 0. Now question is that why copper undergoes disproportionation reaction in aqueous solution? This is the another important question for your time. Why copper positive undergoes disproportionation? Okay. Question is, why copper 1 undergoes disproportionation reaction or unstable in aqueous solution? Very important question. Actually, listen from here. This is copper. It has atomic number 29. Electronic configuration argon 4s1 3d10. So this is the valence shell. Now when copper releases one electron, it becomes copper positive ion. The energy required to release the first electron is called ionization energy or ionization enthalpy, and it's unstable. After releasing one electron, don't write it, okay, only understand, after releasing one electron it becomes stable. So the first ionization energy for copper is low, because from unstable it goes to stable configuration. Now don't write it, only understand. When copper positive ion releases another electron, it's a stable configuration. Again it becomes unstable. So to remove the second electron to change into +2 ion, the second ionization energy is too high. The second ionization energy is too high. Now listen, don't write it. Don't write. This is the only answer, this much. Now listen, when copper positive ion in aqueous solution will change into divalent copper, then the hydration energy is much more negative. The hydration energy is much more negative, which compensates the energy required for second ionization enthalpy. That's why copper positive ion in aqueous solution undergoes disproportionation reaction. So if this question will come, it carries hardly 1 mark, so write up to this answer, okay? This is for your understanding. Don't write it in exam, okay, because time is also vital fact. Now listen, what is hydration enthalpy or hydration energy? Don't write, only remember it. Whenever any compound, if it is a compound, when dissolved in water, it releases some energy, that is called hydration energy. So what is hydration energy? Hydration energy is the energy required, energy released when a compound is dissolved in water. So remember it, when compounds of copper having +1 oxidation state is dissolved, say CuCl, copper chloride, CuCl, copper has +1. When dissolved in water, it readily change into CuCl2, copper dichloride. When copper chloride, CuCl, is dissolved in water, a high amount of hydration energy is released, which is determined in case of electrode potential value. It is so negative that the energy required to remove second electron from copper compensates, the hydration energy compensates the ionization enthalpy of second. That's why copper 1 in aqueous solution undergoes disproportionation reaction, okay? So write only this part, this is very important, this is for your understanding. Listen, the question is, why transition metals have very high enthalpy of atomization? What happens, actually listen, understand it. If we consider the transition metal, the molecules are closely compact due to the presence of unpaired electrons in their valence shell. That's why to break the molecules into atoms, a high amount of energy is required. That's why transition metals have very high value of enthalpy or heat of atomization. That is, molecules, energy required or energy released to break a molecule into atom. So the question is, transition metals have high enthalpy. Enthalpy means heat of atomization. Why? Due to the presence of unpaired electrons in their valence shell or outermost shell, they have very strong intermolecular force of attraction. So to break them, that is to break the molecules, a high amount of energy will require, resulting high heat or enthalpy of atomization. Okay, I think you understand. Listen the question, okay. Actually, you know that there are mainly 3 transition series. Mainly, the last element of the first, don't write, only understand, the last element of the first transition series is zinc. The first transition series is called 3D transition series. The second transition series is called 4D, which has cadmium at the end, and the third transition series called 5D, which has mercury at the end. Actually, they have d orbital, that's why they are treated as transition metals. But some of the properties of transition metals are absent in them. That's why zinc, cadmium and mercury are not considered as true transition metals. Actually, you know that most of the transition metals have unpaired electrons. That's why they are paramagnetic in nature. And due to this paramagnetic nature, most of the compounds of transition metals are colored. But if we consider zinc, cadmium and mercury in their divalent state, that is whenever you release 2 electrons from their valence shell, all the electrons are colored. That's why they form colorless or white compounds. That is, most of the compounds in their divalent states, zinc, cadmium and mercury are colorless or white. Zinc, cadmium and mercury are diamagnetic in nature, as all the electrons are paired, while most of the transition metals or their ions are paramagnetic in nature. So understand this, okay? The question is very important for your time. Zinc, cadmium and mercury are not true transition metals. Explain why. As they have paired electrons in their valence shell, so they have low melting point and boiling point. Why? Due to this paired electron, they have not so strong intermolecular forces of attraction. That's why to break them, low temperature is required, resulting their low melting and boiling point. So due to their pair electron, they are diamagnetic in nature, and thus they do not form any colored compound, while you know that most of the transition metals are paramagnetic and form colored compounds. That's why you can say that most of the properties of transition metals are absent in them. That's why they are not considered as true transition metals. Okay, I think you understand it. So follow the next question. Discuss about the oxidation states of transition metals. Actually, do you know oxidation state is nothing but it's the valency. Nowadays, it's called oxidation state because valency never be zero. In the concept of valency, it is the number of electrons gain or number of electron loses. So valency never be zero, but oxidation state can be zero. That's why instead of valency nowadays it is better to say oxidation state. So most of the transition metals, when release electrons from their valence shell or outermost shell, they generally show +2, +3, +4, +5, +6 and +7 and +8 oxidation states. So these are the positive oxidation states. So transition metals show positive oxidation state of +2 to +8. +8 is the highest oxidation state shown by transition metals. There are 2 elements, ruthenium and osmium. They show the highest oxidation state of +8. Okay, I will discuss the question regarding it. Transition metals also show zero oxidation state in the compounds of specially metal carbonyls. For example, nickel tetracarbonyl, iron pentacarbonyl, etc. You know that compound of metal with carbon monoxide are called metal carbonyls. Transition metals also show negative oxidation state. So far, only one compound of cobalt can be isolated where transition metal shows, that is cobalt shows -1 oxidation state. This is the best known example of compound. See how the cobalt shows -1 oxidation state. Say it is X. Potassium, you know that potassium, sodium, lithium belong to group 1. They always has oxidation state +1. That's why potassium +1 plus cobalt to be find out X plus. You know that carbon monoxide is a neutral ligand. That's why it has 0 oxidation state. So 6 into 0 equal to 0. Therefore, X equals to -1. So you see that in this compound, cobalt shows -1, and this is the only compound isolated so far. So listen, discuss about the oxidation state of transition metals. Transition metals show +2 to +8 oxidation state. That's the positive oxidation state. So the highest oxidation state of transition metal is +8, which is shown by ruthenium and osmium. Transition metals also show 0 oxidation state, that is in their compounds of metal carbonyl, example nickel tetracarbonyl, iron pentacarbonyl, etc. These are the specific number, remember it. Transition metals also show negative oxidation state, but so far only one compound of cobalt can be isolated in laboratory. And see here, cobalt has -1 oxidation state. Now the next question is, why ruthenium and osmium show the highest oxidation state of +8? Remember it, transition metals show the highest oxidation state of +8, not all. Only ruthenium, Ru and osmium, OS, they show their highest oxidation state, that is +8. Not in all the compounds, only in compounds of oxides and fluorides. Why? The question at first, understand it, okay? You know that transition metals show +2 to +8 oxidation states, that are the positive oxidation state. So the highest oxidation state shown by transition metal is +8. But all the transition metals do not show the highest oxidation state of +8. It is only ruthenium and osmium which show the highest oxidation state of +8. You know that there are a variety type of compounds: carbonate, sulfate, nitrate, nitrite, nitrite, sulfite, oxide, fluoride, chloride, bromide, iodide. Variety type of compounds are there, but among all the compounds, ruthenium and osmium show the highest oxidation state of +8 in their compounds of oxides and fluorides. Why? Listen the answer. Don't write, I have already written on the board. Due to very high electronegativity of fluorine, that is 4.0, and oxygen, that is 3.5, they form very strong bonding with ruthenium and osmium. That is one reason. And another reason, due to very smaller size of oxygen and fluorine, they can easily coordinate surrounding ruthenium and osmium. That's why they form compounds like this: ruthenium octafluoride, osmium tetraoxide. See, ruthenium, say X is the oxidation state to be find out. You know that fluorine, chlorine, bromine, iodine, being halides, they all show -1 oxidation state. So 8 into -1 equal to 0. You know that for neutral compound, the sum of oxidation state equal to 0. Don't write, only understand it. So X equals to +8. Here X plus oxygen always show -2 oxidation state. So 4 into -2 equal to 0. So +8. So you see that in this type of compound. Now what happens? Due to very small size of fluorine and oxygen, say if you consider it is ruthenium, 8 fluorine atoms are easily surrounding coordinate surrounding ruthenium. That's why ruthenium and osmium show their highest oxidation state of +8 in the compounds of fluoride and oxide. This is the reason. Due to very small size of oxygen and fluorine, they can easily coordinate it surrounding ruthenium or osmium. Okay, so this is the only answer. If this question will come, only write it. Okay, so listen, why ruthenium and osmium show the highest oxidation state of +8 in the compounds of only oxides and fluorides? Answer is due to very high electronegativity of oxygen and fluorine. The bonds are very strong, they form very strong bonding. Another reason, due to very small size, they can easily coordinate surrounding ruthenium and osmium like this. That's why you can write the example ruthenium octafluoride, osmium tetrafluoride. Only you can write the example, but don't show it. Okay, this question hardly carries 1 mark, so don't show it. It's for your understanding. So I think you understand it. Clear? Listen the question. This is another important question. You know that transition metals show positive oxidation state from +2 to +8. Generally, compounds having the lower oxidation states, that is +2 and +3, are ionic in nature, while +4 oxidation state compounds are amphoteric in nature, and oxidation state from +5 to +8, that is treated as higher oxidation states, the compounds are covalent. Why? Let's understand. In lower oxidation state, transition metals form ionic compounds, while in higher oxidation state they form covalent compound. Explain why. In lower oxidation state, that is in +2 and +3, they easily lose electrons from their valence shell, because you know that the valence shell are very far from the nucleus. So to remove the valence electron, low energy is required. That's why they prefer to lose electron, and thus they form ionic compounds in their lower oxidation states. While in higher oxidation state, that is +5 to +8, they prefer by sharing of electrons from their d orbitals. That's why the compounds of higher oxidation states are covalent in nature. Okay, so if this question will come, right up to this only. Now let's understand the next question. Discuss about the magnetic properties of transition metals. Okay, most of the transition metal and their ions are paramagnetic due to the presence of unpaired electrons, but zinc, cadmium and mercury are diamagnetic in their +2 oxidation state, as all the electrons are paired. If we consider any transition series, the paramagnetic nature reaches maximum at the middle, then starts to decrease. So I think you understand it. So listen the conception regarding it. Magnetic nature in chemistry, don't write, only listen. Magnetic nature in chemistry means whether the corresponding ion in a compound is paramagnetic or diamagnetic. You know that most of the transition metals or their ions in compounds contains unpaired electrons in the valence shell. That's why they are paramagnetic in nature. And as we proceed from left to right in any transition series, the number of unpaired electron in plus 2, if you consider plus 2 oxidation state, the number of unpaired electron increases, reaches the highest and then starts to decrease. That's why it is said that in a transition series the paramagnetic nature increases, reaches maximum at the middle and then starts to decrease. Okay. The paramagnetic nature or paramagnetic character, which is called paramagnetism, can be calculated numerically in terms of magnetic moment. That's another important question, magnetic moment. So remember it, the paramagnetic nature or paramagnetism can be calculated in terms of magnetic moment. Okay, so the question is, calculate the spin only magnetic moment of Mn plus 2 ion. Okay, calculate the spin only magnetic moment of manganese plus 2 ion. Sometimes the atomic number of manganese is given, sometimes not. So you have to remember the atomic number from scandium, that is 21, to zinc 30, remember it. 25 atomic number is given, but sometimes if it is not given, you can't write the answer. So the answer, you know that magnetic moment, that is denoted by mu, equals to root over n into n plus 2 bm. Bm is the unit called Bohr magneton. Bm is the unit of magnetic moment called Bohr magneton, and n is the number of unpaired electron. N equals to number of unpaired electron. Okay, so how to write the answer? At first, write the electronic configuration of manganese. You know that manganese has atomic number 25, and write this way: argon 18, 4s and 3d. 4s contains 2, 18 plus 2, 20, and the rest 5. And remember it, this is the valence shell, this is the valence shell, this is the outermost shell. Now in manganese, 2 positive ion, remember it, electrons at first removed from the valence shell. So argon 18, 4s 0, 3d 5. So d orbital, you know that there are 5 d orbitals. Okay, put 5 electrons according to Hund's rule. Electrons at first filled singly with parallel spin. According to Hund's rule, electrons at first filled singly with parallel spin. So the number of unpaired electron in divalent manganese is n equals to 5. So put into it. So magnetic moment, that is mu equals to root over 5 into 5 plus 2 equals to root over 35 bm. That's the answer. Okay, this is the another important question. So I think you understand it. Okay.